Students often get questions like this wrong, and it's because they forget that poles are not charges. That south-seeking pole on the magnet is not a negative charge, and electric forces are not magnetic forces. There is a force exerted by these two objects on each other, but it's an electrical force. Just like anything else, that negative charge will polarize the magnet electrically. And just like any other object that it polarizes, it'll attract it. But that's an electric force, not a magnetic force. And the question is asking about the magnetic force. There's no magnetic force here at all. Magnets do not exert magnetic forces on stationary charges. Just as we were able to understand charge in terms of electrons and protons carrying elementary charge, we can understand magnets in terms of the magnetic properties of the particles they're made out of. It turns out that every subatomic particle, electrons, protons, and neutrons, is just like a very tiny bar magnet with its own north-seeking and south-seeking pole. The way those combine together in atoms is rather complicated. You may have learned a little bit about it in a chemistry course, but the result is that many atoms themselves are magnets, and these are what we're going to refer to as the elementary magnets that a material is made out of. So now we can understand that in a magnetized object, the elementary magnets, which I'm representing as these little half-filled circles, are aligned. Whereas in an unmagnetized object, the elementary magnets are randomly aligned compared to each other. In fact, it's more complicated than this. Even in a magnetized object, there's a fair bit of disorder in the organization of its elementary magnets. But the more aligned they are, the stronger the magnet is. We can also now see why it is that we get two complete magnets when we cut a magnet in half, because clearly each half still has aligned elementary magnets, and so each half will still have a north pole and a south pole. Magnetic forces are long-range forces, and so just as we've been understanding electric forces using a field model, we can use a field model for magnetic forces as well. So it's time to talk about magnetic fields. We'll start by defining the direction that a compass points as the direction of the magnetic field at the location of the compass. So if we wish to map out the field around this bar magnet, we could place a compass near it. Clearly, the south-seeking pole of the compass is going to be attracted to the north-seeking pole of the magnet, and so that tells us the direction of the magnetic field, which we'll represent with B, at that location. We can then place the compass at other locations and find the B field there. Everywhere we place it near the north-seeking pole of our bar magnet, the field will point out away. And similarly, anywhere we put the compass near the south-seeking pole of the bar magnet, the north-seeking pole of the compass is going to be attracted to the bar magnet, and so that tells us that the B field points in towards the south-seeking pole of the magnet. Similarly, we can map out the field in other places and draw a vector diagram. Note that this only tells us the direction of the magnetic field, and so this is nowhere near a complete definition of magnetic field. This definition, though, is enough for us to be able to draw magnetic field lines, and we'll do it in much the same way that we drew electric field lines by moving a probe charge in the direction that the force acted on it, only now we're moving the compass in the direction that its north-seeking pole points. And so we move it in small steps, drawing the line as it goes until it maps out a complete line. That line must leave a north-seeking pole of a magnet and enter a south-seeking pole. Note that every north-seeking pole has a partner south-seeking pole, and those poles have to have the same strength, whatever that means. We don't really have a definition for the strength of a pole, but the pair of poles must have the same strength. And so we'll draw the same number of lines coming out of each north and going into its partner south. That number, just like with electric field diagrams, is arbitrary. And once again, the density of the field lines is proportional to the field strength in that region. Note that this is essentially what happens in the familiar experiment where you take a magnet, put a piece of paper over it, and sprinkle iron filings on. The filings align with the magnetic field and essentially draw out a field line diagram. You'll hear people make the claim that the filings are in fact following individual lines, but remember, the number of lines in a diagram is purely arbitrary. The lines don't really exist. They're a drawing convention that we have made up. The reason the filings seem to make lines is that they are magnetized by the field they're in, and so they exert forces on each other, and that tends to make them line up end to end. Note that the field due to a bar magnet looks an awful lot like the dipole field due to an electric dipole. These look very similar, but don't be fooled. There are enormous differences between them. First of all, the field lines have totally different meaning. You know that the electric field lines indicate direction of electric forces. The magnetic field lines are actually more complicated. We'll see how the magnetic forces are related to the lines, but they aren't as simple as they were for electric fields. Also, the field due to a bar magnet isn't truly a dipole field. You can think of it as if you've got a north pole and a south pole, and those are sources of the field, but that's only an approximation. Remember that what's really going on is that you have a collection of elementary magnets. Each of those elementary magnets does produce something that really is a dipole field. The total field of the bar magnet, though, is the sum of all of those dipole fields. And that makes it very similar to a dipole field, but the sum of dipole fields due to dipoles at different locations isn't quite the same as a dipole field. We've been able to get away almost entirely with diagrams where the vectors, no matter what vectors they are, force vectors, field vectors, acceleration vectors, whatever, have been in the plane of the page. However, that's about to change because magnetic fields and magnetic forces are relentlessly three-dimensional, and so we're not going to be able to avoid vectors that are perpendicular to the page. So we need a convention to represent them, and there's a simple convention. We draw a vector coming out of the page simply as a dot. And we draw a vector into the page as an X. Note that sometimes it's useful to be able to use dots and X's to indicate just places in a diagram, and then that can get confusing if you're also using dots and X's for vectors out of and into the page. And so an alternate convention that I'll often use is that a vector out of the page is a dot with a circle around it, and a vector into the page is an X in a circle. Just as we did for electric fields, it's going to be useful to define a flux for magnetic fields. And just as with electric flux, we started off by looking at field line flux, we're going to start off by looking at a field line flux here. So that's just the number of lines passing through a surface we've drawn. And for closed surfaces, like this purple one I've drawn, we'll use the same convention, that lines leaving the interior contribute a positive flux, so in this case there's a positive 3 flux from those points, and lines entering the interior contribute a negative flux. So for this surface there's a negative 3 here, and so the flux through this surface is 0. Well, what about this surface? It's tempting if you just count the lines on the diagram to say that it has a field line flux of plus 8. But that's actually incorrect, and here's why. Remember that what's really producing the flux is all those elementary magnets inside. And so at every point, we have to sum up the fields due to those elementary magnets. But there's no reason not to do that inside the bar magnet as well, and so the field lines actually continue through the inside of the bar magnet. And now if you count, you'll find that the flux is again 0. You can see that this has to be true in another way. Every elementary magnet is either entirely inside or entirely outside any surface that we draw. And every elementary magnet has to have an equal number of lines leaving it and arriving at it. And so that right there tells you that the magnetic field line flux through any closed surface is always 0. That's rather interesting. It means that closed surfaces don't give us quite such a useful law, like Gauss's law, as it did for electric fields. And so most of the time, we're actually going to be more interested in non-closed surfaces when we're thinking about magnetic flux.